right, good. We're on live. So here we are. We are in the second review session here at the wonderful Music Suite in Windsor. Thank you to the music. Oh, that's killer. Thank you to the music department for letting us hang out here. If you haven't already, you can grab a chair. You can grab a music stand to write on. Here's what I was thinking. This session is going to kind of go as long as you want it to, and if you want to leave it anytime you can. That reminds me, if you are watching online, where did it go? There it is. You can tweet in a question. You'll see right down there is the Twitter handle. There's also a cell phone number down there that you can text. It'll ring right here. I'll know. And if you're sitting there thinking, ooh, we'll send them a text later. No, I turn off the phone number so it doesn't work. I never emailed you an answer. Yeah, you want her. So we'll talk. Okay, and we'll make sure that comes up because I remembered that. You know what I'm talking about, right? Okay, yeah, I never got back to you on that one, so I want to make sure that's good. My fault. That's what I'm talking about, right? That one right there. So we can go back and look at that and see what's going on. Oh, that's you.
Yeah, but you can't email me because I made a fake email when I made that Twitter.
Okay, so do you have that exam with you?
Yeah.
Okay, so we can still talk about it. That'll totally work. I'm sorry. So that's why you, the first one, were looking at me so funny. I thought that was you the whole time. Okay, right on. So good deal. Good deal. Okay, so here's what I was thinking. Last time when we did this, I just said, okay, what things do you want to talk about? What material? What units? And everyone was kind of, and then what it very, very quickly devolved into was, what about this question on the Regents? What about this question on the Regents? And it just turned into a Regents like marathon. So what I thought we could do is, if you want, we can either look at particular units, or we can just dive right into the exam and see what comes up from there. So obviously, if you're watching at home, you can't vote right now. But how about from you guys? How many people want to go like try and talk about a particular unit? Okay. How many people just want to go through the exam and we'll kind of talk about the units as they come up? Awesome. I think we're going to go that way. So make sure when the question comes up, for the people that wanted a particular unit, just make sure you ask the question about that one, and it'll work out fine. And if you're watching at home, make sure you just, tweet in a question like, hey, can we look at number so-and-so? So it just so happens, let's get off my ugly mug here. I have, there. Why did you ding? Don't ding. I don't care. Okay. So there's the exam, and I can look at it here. We can talk about questions. So let's just go question by question, and we'll think about 10 question blocks, and we'll go from there. So again, this is the, which one is this? The June 2013, which I think is the pink one in your packets. Yeah, I didn't bring reference tables. So if you have them, we can use them. I can also pull them up on here and we can take a look. So let's just go in 10 question blocks. So 1 through 10. What do you got?
Wait, what one are we doing?
The pink one, 2013-ish. 1 through 10. You didn't have to, but that's kind of like the way we can talk about it. So yeah, go ahead. What do you got?
4.
Number 4. Okay, so I'm really hoping with number 4, you were stuck between number 3 and 4. Good, because protons don't move. Okay, and this came up the last review session too on Wednesday. The bright line spectrum from an element, this is the excited state and the ground state, and I think someone last time was saying, I just don't understand what the difference is. Everything is exactly the same between a ground state and an excited state. The number of protons, the number of neutrons, the number of electrons, it's all the same. What's different is the organization of the electrons. In a ground state, they're packed from the bottom level up. And the excited state is anything different. So if you skip a level or if you don't fill it in correctly. So everything on your reference table is all ground state. I know that's a lot more than this question has to deal with, but that's the kind of stuff that as we're going through it, if you say, wait a minute, what's this again? We can go off track with these questions. That's the point of it. That's kind of why this one goes so long. So let me hide that though. So like I was saying, sorry, protons definitely not moving here. Hi. Electrons are moving, and they go up to a higher level by absorbing energy. It could be lots of different forms. It could be electrical energy, which is, if you remember the tubes that we had in the auditorium where we put on the funny glasses, right? That was using electricity to make them move. We could use fire, like when you put the sticks in the fire and it made different colors. You could use all sorts of different stuff. But when that color is given off is when the electron goes back down. Because if you think about it, to move up, it has to absorb energy. So when it comes down, that energy goes back out, and that's the color that we see. So for this one, it's going to be choice 4 when they go from a higher state to a lower state. Okay. Others 1 through 10. Yes. Yeah, let's keep rolling.
5.
Okay, so here's the deal with this one. This is a good time to start drawing. Lithium, this 7, right? Do you guys all know what that 7 is? I think I heard it. It's what? It's the mass, right? It's that top number. So that's cool. The bottom number is the one that we can look up on the reference tables, which I think for lithium is 3. So that tells me, you guys remember what that bottom number tells you? That's just the protons, right? And the top number tells you protons and neutrons together. So if I think about this, I know how many protons does this have? 3. And that makes sense, right? You're cool with that. Now neutrons, that's going to be in this case 7 minus 3, which is 4, right? So I already know that number 3 is out because they don't have the same number of protons and neutrons, right? Oh yeah, thanks. We'll bring 3 back into the mix. That actually makes this question really easy. I didn't notice that because positrons aren't in atoms, right? What's in an atom? 3 things. Protons, which is what I thought that said. I heard the other was electrons, protons, electrons, and neutrons. So 3 and 4 are gone because positrons aren't in an atom. Right?
What are they?
Was that you? Okay. They're a negative electron. They're part of nuclear chemistry. Let me rephrase that then. They are an inverse electron.
So they're positive?
Yes. Do you have a reference table?
Yeah.
Okay, check out table O, and you'll notice a beta particle is the same thing as an electron. And if you look at a beta particle and a positron, they're exactly the same thing, except the charge on a beta particle is -1, and the charge on a positron is +1. But they both have 0 mass. Yeah, you'll get there.
Well, it's a lot of order, so I don't think
It's okay. Well, when you find it,
Got it.
yeah, there you go. So you see beta particle. I think it might be the second one down,
Yeah.
and then positrons all the way at the bottom.
Yeah.
They're almost the same, except one is -1 and one is +1. So a positron is an inverse electron. Okay. So to wrap this, the question is, and was it dealing with what I talked about, or is it a new question for you two?
It has to do with that.
Okay, and your new question. Okay, so with this, and let me see if I answer it, and if not, let me know. Okay, the electrons. What the heck? How many electrons are here? The key word, we talked about this the last week of school, is atom. Right. So what does that mean? It's neutral, which means the protons and the electrons have to be the same. Right. So in this case, it should be choice 2. The electrons and protons are the same. That's true because we also talked about this on Wednesday in the review session. Any atom will always be neutral. Ions have a charge. Atoms are neutral. Okay. So did I get it, or is there still more?
I have 2 questions.
Yeah. It's okay.
So the positrons are only found in nuclear chemistry. Like you won't, if it's anything that doesn't have to be nuclear, it
Correct.
won't be the answer.
At this level, yes. Yes.
And then if an atom means neutral, what would it be if it did have
Ion?
Okay.
And sometimes, yeah, they get around it because they'll say an element of, which of the following is true for an element of chlorine, and they'll show it with a charge. So element is what element it is. Is it carbon? Is it sulfur? Is it oxygen? Is it nitrogen? Atom is neutral. Ions are charged, like guaranteed. If they say it otherwise, they're wrong. Okay. I'm going to go, well, you had one, right, in front.
Yeah, it's different.
Okay.
About this.
Okay, let me get that one, and then we'll come up to you.
Okay, so an ion doesn't have to be in an excited state, then, right?
Right. Okay, so let me come back to that. That's a good one. Excited state, you don't gain or lose anything. It just moves. Ions, you either gain or lose something. So the number of electrons and protons will always be different in an ion. Depending on which charge it is, you could have more electrons or more protons, right? But in an excited state, there'll always be the same total number of electrons as in the ground state.
Okay.
Same material, I'm guessing? Yeah, keep going, shoot.
Does an ion like have to be bonded to something?
Nope. 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 Doesn't have to. It can be free floating. That's how salts and electrolytes conduct electricity, is because they have ions that are free to move. When they're technically they're bonded, but they're free moving. Whereas do you remember the light bulb that we put in salt and it lit up, but when I put it on salt on the desk, it didn't? That's because those ions, while they're bonded, they're stuck to each other and they can't move. In water, it's technically still bonded because it's a physical change, not a chemical change, but they're able to move around. Okay, let's come up. Is it the same or new?
No, it's a question.
Okay.
Why is there 3 electrons?
Because it's, ow, oh, that wasn't fun. Because it says the word atom, and atoms have to be neutrally charged. So since protons are positive and electrons are negative, they have to have the same number if it's neutral. Okay, so let's come up front. Let's get this one. Number 8, all really good questions so far. Clean this up. There's got to be a better way I can wipe the slate clean. Okay, 8. Which element is perfect? Oh, okay. So this is one of those answers that when you see it in short answer, like when it's 51 through whatever, you always want to give 2 responses for why these 2 elements have similar chemical properties. Same group, same number of valence electrons. So what you're looking for here is something that's in the same group up and down as fluorine, which should be choice 2, chlorine. The way they made it a little tricky is they gave you, I think, boron and oxygen are in the same period. So they're in the same row. And in fact, neon, I think, is in the same period as well, the same row. But chlorine is up and down. So kind of, if you forget which is which in that case, you might say there's 1 that's in the same up and down, but 3 that are in this, it's got to be that one because that one's different. But yeah, it's looking for the same group. That's what you're looking for. Good. Yes, ma'am. 7. Neon. Okay. So were you stuck? Did you not know? And I'm asking because it depends how I explain it.
Well, yeah.
Okay. How did you go for it? Like, what did you think?
It's not 1 or 2, right?
Okay. How come?
Well, because I don't know.
Well, because are only the things in 18 gases? Yeah. No, tons of other things are gases. So that's out the window. How about what is group 18? You remember? Keep going. It's 1 more. Yeah, it's the noble gases. It's that way for you. Sorry. It's the noble gases. So those are the ones that have that full outer shell. They don't want to bond with anything because they have 8, right? So that's what it's all coming down to is number 3. So number 2, the low melting point, that, woo, big deal, right? Lots of things have low melting points. Number 4, neon atoms have 2 electrons in the first shell, but so does most everything else except for the first 5 elements. Oh. No, everything except the first element, hydrogen. Everything else has 2 electrons in its first shell. So it's all about that stable configuration. They got away from 8, and they just said stable. But having 8 in the outer shell, the valence shell, that is as stable as you can possibly get. Okay. Awesome. Yes, ma'am. 9, sure. Oh, okay. Did we talk about BARF on Wednesday? BARF. I know some of my classes did, some of my classes didn't. BARF is an awesome acronym, and what it's all about is this. BARF, right? BARF. Breaking, absorbed, released, formed. BARF. Right? I picked this up like the last 2 weeks of school. When you break a bond, energy is absorbed. The way I told you guys that is with a pencil, right? You got to put energy in to break a pencil. So when you break a bond, energy is absorbed, and it's released when a bond is formed. So kind of what I'm thinking is if I start with that, I forget, where did this question come from? That's what I thought. Okay. If I think that breaking is absorbed, that means out of 3 and 4, it can't be 4, right? right? Because breaking is absorbed. And if I think about the RF, released is formed out of 1 and 2. It's got to be, it can't be 1. So now I'm down to either 2 or 3. Those are the only 2 logical statements. And it says what occurs when 2 atoms of fluorine combine. So if I take 2 atoms and I make them into a molecule, is that breaking a bond or making a bond? Yep, it's forming one. So totally choice 2. Energy is released. Barf. Barf. Can't go wrong. Right? Cool. Do I have signal in here? Yes, I do. Good. Other things 1 through 10. Awesome. Sorry? Number 10. One number of pairs. Okay, so this is kind of tricky. So if I think about nitrogen, it has 5 valence electrons, right? So if I take another nitrogen and I make another 5 valence electrons, because that gets me the N2 that they said in the question, I want to pair up all these single electrons, right? So if I do that, I got 1 pairing there. I got 1 pairing there. Can you see over my head? How's that? And I got 1 there, right? So that, just for the record, that makes a triple bond. Okay. Now it wants to know, and the thing you have to be careful of with these questions is sometimes they're going to ask how many pairs of electrons, which is what they did this time. Sometimes they ask how many electrons. So it's either you're counting the electrons or you're counting the pairs. In this case, there's 3 pairs, right? So 3.
How would you draw that?
Just like I did. Or, so if I was going to draw this, I know what you're asking. I could take these 3 electrons right here and these 3 electrons right here and move them into the middle because they're all sharing. So what that would end up looking like is 1, 2, 3, right? Those are the 3 that I moved, and then the 2 that stay there. And then 1, 2, 3, and oh, I'm sorry. There we go. Is that better?
Yeah.
Awesome. Can you see over me? Okay. And you could technically leave it like that and be okay. You don't have to draw in the circles with this one. But if you wanted to, it would look like that.
Okay, thank you.
Yep. So I think that was almost all of them, but that's good. I like questions.
Would that ever be a short answer?
Yep.
To draw those little things?
Well, what about the ones that have like
a Lewis dot
it's like there's more than just the 2 of the same elements. Like if we like another one in there.
Yeah, no, I know what you're talking about. Usually when they do that, they say draw the Lewis dot diagram for the ionic compound MgO. Okay, so what you would want to start with
They
is,
usually have more things.
well, at most it's going to be 4 things.
Right.
Right.
Well, I can do it too. I can't do it.
Yeah.
Well, then let's go complicated. And let's do.
Let's
I think the one they had on a test was CH3Br.
sounds familiar.
Okay, so carbon's got to be in the middle. Usually the first thing that is not hydrogen goes in the middle. And how many bonds can hydrogen form? 4. So even though the dots would go 1, 2, 3, 4, right? What I'm going to do is this. I'm going to get rid of that one and put it over here because I know it can make 4 bonds. So I'm going to have to split that double up. And then I need 3 hydrogens. So do you guys remember how many valence electrons hydrogen has? Okay, so I'm going to put 1 here, and I'm going to put 1 here, and I'm going to put 1 here. And then I need bromine. So bromine's in group 17. You know how many valence electrons that has? 1, 2, 3, 4, 5, 6, and 7. Now, technically speaking, I could leave it there and I'm good. Honest to goodness. If I wanted circles, 1 there, 1 there, 1 there, because hydrogen only wants 2 electrons, right? And then with this one, I got to grab all 8 there. And then I need 1 for carbon, which would look something like that. because that has 8. The thing is, you don't really need the circles, and I almost would suggest not putting them in, because if you draw them in the wrong way, or if you don't put enough electrons in, like, that's okay, except that I just erased a dot, but you get the idea. That'd be fine, right? You could also, the other way they allowed it was that. Yeah, but the key is you had to have all the dots on BR. Because if you just left it like that, that's not okay. Because the electron dot diagrams are showing where the dots are moving. So in that case, hydrogen is sharing it on all sides, and then the bromine is only sharing that one. So the other ones have to be shown. Whoa.
And hydrogen would never be drawn in the middle.
No, because it can only form one bond because of that one electron. Okay. Gesundheit. Cool. So I'm not seeing anything online, which is cool. What I'm going to do though is just come back here for a second so people can see, because it's not showing up. There it is. If you have questions, you can tweet down at the bottom. I'm going to get a drink of water, and you can see me and me and me. And there's a cell number down there too. If you have questions, feel free to text in. But that was questions 1 through 10. Were there any others in 1 through 10 you wanted to talk about? So far, it's all been very good questions.
Number 1.
Number 1, sure. Let's go take a look at that. Doodle 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 doodle. Oh yes, because see, that's the answer.
That was our question.
Where you can, I know there's at least one person in this room that can tell me where to find this, and that's you in the back. Yep, you. No, this one. Yeah, you. Because I can't say names if you came in late because it's online. But you know where to find this answer, because I always say it's on table. It's the table. When you figure out that's where to look, you go. Oh, see, yeah. Oh, table. Oh, because I don't think he remembers. He was always the one that went oh in class. So it worked out. Right? That's what happens when you're gone for a week. So where, I forget, where did this one come from? Was it okay? Table O. Right? You want approximately the same mass. So that's the top number on table O. And the reason they have to say approximately is because a neutron doesn't really weigh 1. It weighs just a little tiny bit more than 1. Even though the number is 1, it's really 1 and 1/1836. So, but it's really close to 1. So that's, if they said exactly the same mass, people like me would say that's a horrible question. You should throw it out because there isn't a correct answer. And then they'd have to deal with that. So that's why. So anyway, what you're looking for is the 2 that have the same top, which alpha particle has a top of a mass of 4, beta particle 0, so that doesn't work. Alpha particle is 4, proton is 1, that doesn't work. Neutron is 1 and a positron is 0, so that doesn't work. But a neutron and proton, yeah, number 4. They're both a mass of about 1. Anything else through 10? Yes, ma'am.
Could you go over 6 a little bit?
6 a little bit. So the first word is in.
Yes.
There, I went over it a little bit. Okay, the second word is which. Okay, so here's what I'm thinking with this, right? When I see which type of chemical reaction, I know like fusion, fission, transmutation, they're all out the window because those are nuclear reactions. So, and it gives me a bunch of choices. So it says, where do you, in what reaction do 2 or more reactants combine to form? So what if I do this? Because that's kind of what it's talking about. And I like number 1. Okay, number 2 is the opposite. That's going from, I'll say less things to more things. It's breaking things apart. Number 3, you got to have things switching, and nothing's really switching here. And then so, same with number 4, they have to switch. But the difference, single replacement, you start and end with a single element. So that's why it's synthesis. You're making something new. Does that work okay for you? Yes, ma'am.
What's answer number 3?
One. I think we got all of them, but I'm not sure.
Maybe we should just go.
No, it's going to take forever to go through for every single one, but if we have to, we will. It's okay. Can we do what? Sorry. 2.
And then we do all the one we did. Yeah.
That's the one we didn't do. So heck, let's do it. Okay. So which phrase describes an atom? The nucleus has to be positively charged. So I'm hoping you maybe were between 3 and 4. Okay, because here's the thing. If you think about an atom, it's got, well, we said earlier, what are the three things that make up atoms? Protons, neutrons, and electrons. Protons and neutrons are in the nucleus. Okay, so you got positive things and things that don't have a charge, which means overall the nucleus is positive. And then you got the electrons spinning around on the outside. So this is all about number 4. And you know, if you think about it, even if you weren't sure about the nucleus of an atom, I know that electrons are on the outside, and I know that electrons are negative. So for that reason, I gotta go with choice 4. Everything else has it all sorts of whacked out. Okay. Sometimes it's just seeing that and going, oh yeah, that is easier than I thought. So let's open it up a little bit. Let's go through 20. Through 20. Yeah. 12. Which statement about one atom of an element identifies that element? Okay, we just said like 4 different times, the 3 things in an element, that's okay, are protons, neutrons, and electrons, right? And we kind of talked at the end of the year that atoms are just, elements are just globs of protons, neutrons, and electrons. But the key is, what makes an element an element? It's the number of protons. So knowing that now, it's got to be number 1, because nothing else matters. In terms of what makes it one element from another element, it's always the number of protons and only the number of protons. Little review for everybody else. What's it called when things have a same number of protons but a different number of neutrons, meaning a different mass? Isotopes, right? Same element, same number of protons, different number of neutrons, different mass. What about if it's the same element but a different charge? Those are the ions that we talked about earlier. So that's why this one's all number 1. Okay. Others through 20. Yes, ma'am.
I was going to ask what an isomer is.
So an isomer, that's organic, right? The carbon stuff with all the chains. It's a similar idea. Iso means same. So it's the same stuff. And not only is it the same stuff, it's the same exact number of things that make it up. So it's like, it's got to be 4 carbons and 6 hydrogens and 2 oxygens or whatever the heck it is. But they're put together differently. That's what an isomer is. Same stuff, same exact stuff, put together differently. Others through 20. Yes, ma'am, in the back. 16. Oh, okay. So you could do this a couple different ways. And the easiest way is to realize that this is a definition, but I never really addressed this with you guys as far as the definition, right? So if I were to say, okay, total amount of heat, right? Can you see this back here? Is that cool? Okay. So total amount of heat, those are those equations, right? Q equals MC delta T, Q equals MHF, Q equals MHV. And if I'm vaporizing, right, that's going to be Q equals MHV for vapor. Yeah. And then, so if you look at the front of your reference table, HV is the heat of vaporization, which is 2,260. On table B, you got it? Okay, so that's actually the definition part. The total amount of energy required to evaporate or vaporize 1 gram of water at 100 degrees Celsius, 1 atmosphere, that is the heat of vaporization. So it is 2,260. But even if you didn't quite get that connection, which I don't know if people would, if you plug in the numbers, you get 1 times 2,260, and that's your answer. So that's why I say there's 2 ways you could have done it, but either way gets you at number 4. Yeah, sure. Others through 20. Yes, sir.
So on that question, the temperature doesn't
matter.
It depends.
The temperature matters because 2,260 is the amount of energy it takes at 100 degrees. If it was warmer or colder, it's going to be a different amount of energy. But we don't really get into that here in Regents. Like if they're doing an equation, a problem like this here, it's always going to be 100 degrees in 1 atmosphere.
Wait, what was the one part that you multiplied?
Because the mass is 1 gram, so it was mass times 2,260. So, and the mass in this problem is 1 gram. So that's why it worked out. So yeah, I want to go here, and then I'm going to go right down the line.
So are they going to be in right relationship to I know you said it's always going to be.
I don't know. I don't know. I didn't study that a lot in college. I don't know if it's going to be direct, but it'll definitely be related. You know, but I just don't know which way, and I don't know if it's proportional. I want to say it is, but I can't say that with certainty. So then we go to, sure, why not? 15? Okay. Ah, yeah. So I need energy, right? And they didn't give me the easy one of like kinetic and potential, but here's what I can tell you. As I look through these different choices, in number 1, the problem with that is exothermic. What does that mean? It releases energy, right? That's not a form of energy. That's what it does with the energy. So that one's gone, okay? In number 2, I kind of like all of those, and I'm leaning toward that being the answer. Number 4 is out for endothermic. So now my problem is 2 and 3 both look good. There's got to be a reason. It's number 2, isn't it?
Yeah.
Because temperature is not a form of energy. Temperature is a measurement of energy. Okay. I can't give you a good analogy for that one because everything that's popping into my head doesn't make sense. But temperature is a measurement of energy. It's not a form of energy. That's why number 3 is out. Okay. And then I want to go now back if you still had a question. Yes. And then up. 18?
Wait, mine was about this.
I'm listening, and then I will get 18.
Okay. Like, what are like other forms of, and like, is there like a bunch of them?
Almost endless, yeah.
Okay.
It's what they're really looking for with this one is what's not energy.
Okay.
So like I said, number 1 and number 4, exothermic and endothermic are directional terms for energy, whether energy is going out or energy is going in. And with number 3, temperature is a measurement of energy. It's not actually energy. Same question or?
Sort of.
Yeah.
So if temperature is replaced with heat, that would be like.
That's what thermal is. Heat would be acceptable as well, but thermal is the fancy word for heat. Yep. Okay, so 18 is up here. Oh, okay. Do you have a reference table with you?
Yeah.
Is it table F? Is that the solubility table? That you had to know to look there. And if I want the one that's, I can already tell the answer is 3. And the only reason I know that is because I know that everything in group 1, like that's the first thing on the left-hand side, group 1 is always soluble, right? There's no exceptions. And in this case, Na, how come I'm not writing? Na is in group 1. The other stuff, I bet if you find, I think S is on the soluble side or insoluble side? Sulfur, S? Sulfide is which side?
Insoluble.
Okay, and lead is not going to be one of the exceptions, so that's not soluble. Same thing with oh my God, they made this really easy because everything is sulfide. So you just had to find which one was the exception, right? That was easier than I thought. Usually it's all different stuff that all comes in together. Same question or different question?
Different question.
Okay, so let me come up because you had one too.
Wait, why is it sulfide?
Yeah. Yeah.
It was already answered.
Okay, why is it what?
Sulfide.
Because every single one of these has S.
Yeah, but
So it's sulfur, when it's bonded with something, it turns into sulfide. The same way chlorine turns into chloride. The ones that don't change are polyatomic ions. And that's why they don't end in "ide," so the name tells us that it's a polyatomic ion. So back to you, ma'am. Ooh, yeah.
can you go over 14?
Solid element. Okay. So because of this part right there, a good conductor of electricity, I'm going to say it's probably a metal.
Yeah, that's what I thought. I was just making sure.
Yep. Also, the malleable kind of tells me it's metal, but really the good conductor tells me it's not going to be a non-metal because they're horrible. And same thing with noble gas, they're horrible conductors. Metalloids are kind of like, they're right in between. It depends. But because it's that malleable and a good conductor, that's setting me up to be a metal. Yeah. So let's go here and then back. So yes. Yep. 13. 13. So, as either an element or a compound. Why? So substances have to be the same no matter where you find them. So like, not only are they made up of the same stuff, but it's the same. I think we talked about it Wednesday. It's that definite ratio idea. And so, but substances have to be exactly the same throughout the entire sample, regardless of where you get them. So elements and compounds both fit that mixture, or that definition. Mixtures don't, because they're always going to be a little bit different. Whether it's homogeneous or heterogeneous, doesn't matter. Solutions are a type of mixture. So that's why solutions out. Okay. And then 2, I think, was here. 19. Okay. So the only difference between these two is size, right? One is 26 grams and one is 52 grams. So they're going to have the same density because even though there's more of it, it's going to take up more space. Density is always the same throughout a sample of substance, like we were just saying, an element or compound, always going to be the same. A different gram formula mass, that's the molar mass, that's the mass of everything added up, which if it's the same compound, that should be the same. They should have the same chemical properties because it's the same stuff, right? But their volume is going to be different. One is, since you have more of it, one is going to be greater. So compared to this, they got to have the same properties out of that list.
What's that?
Hmm?
What did you say the answer was?
Number 3, they have to have the same properties. They're the same stuff. Even though it's more of it, it's going to have the same. That's like if you have a single popsicle stick, it will light on fire. If you have a room full of popsicle sticks, it's still going to light on fire. Right? It doesn't matter how much you have. It's going to be the same properties. Okay. Same stuff or different stuff? Different stuff. How about yours? Different. Okay, because let me come over here because I got a little bit of an order. So yes, ma'am.
Mine's kind of like this.
I'm listening.
We're talking about like the same properties and stuff. There's usually a question about like carbon, like the
Allotropes.
graphite.
Yeah, they're called allotropes. They have, so
It's like diamond and graphite.
oh, I know. I'm just trying to think of what word I want to say. Definitely physical properties, right, are determined by the structure. They usually with that, they're going to just throw out the word properties, but it's really physical properties. Okay, it could be chemical, but it's going to be physical. So the way it behaves is determined by how it's put together. So that means in those questions, I know exactly what one you're thinking of. No matter what, the properties are either the same because the structures are the same, or the properties are different because the structures are different. You can't have them flip-flop. You can't have same structure, different properties. Like that doesn't work. So when it comes to those questions, allotropes, graphite, diamonds, buckyballs, or oxygen and ozone is another example. They have different properties because they have different structures. Okay.
And then I had another one that was like back to question 14.
Okay.
What are like common like characteristics of a metal?
Of a metalloid?
Yeah.
Little bit metal, semi-metal. So it could be a mixture. It really depends. Like it could be gray, which is metal, and it could be brittle, which is non-metal. But it could be shiny, which is a metal.
So it has someone going.
Yeah. Yeah. Yes, ma'am. We're gonna go back and then front. Yes.
It was kind of like Matt's question. Like, how do you know if it's the structure of the
Usually what they're gonna, the way they key that in is they say carbon can take the form of, so they're saying it's just carbon. It can be graphite or it can be a diamond. And if they're even nicer, they'll say pure carbon. So that's kind of giving you the indicator that it's the same stuff. So it's got to be different put together. You don't necessarily know it unless someone like me showed you pictures of it, which I did. But it's not necessarily expected to be known right now. But when you have a pure substance that is different, it's got to be because it's put together differently. Okay. So up front.
22.
22? Oh, okay. This is a little bit different than I bet a lot of people that took this test and got it wrong said choice 3, because we're like ingrained. They're talking about electronegativity, and they always ask which one's strongest. Fluorine strongest. Boom, done. The problem is they ask which one's weakest. So you can look up the electronegativity and see which one's smallest, because that's on table S. But I'm leaning towards number 2 being the right answer without looking at them. I don't know if anyone can confirm that or not. Because they're both in group 2, but calcium's further down, which means it's bigger. So it's holding onto those electrons less because they're further out. So that's why I'm leaning towards it being calcium, but no guarantee there. But you can definitely look it up. Yes?
When you pick one that's like farthest away from chlorine,
Yeah.
and then like boron and nitrogen are like over on this side and the
Is boron over there? I was thinking beryllium. That's why. I was thinking Be. Is B in group 13?
Yeah.
Okay, yeah. So then even for more reason, calcium wins. Yeah, my bad. It's been a long day. Others through, well, I think we were through 20, but it seems like we've gone over a little bit. So how about through 30? Okay. You were thinking, is it a little bit further along?
No, it's not 4.
It's what?
7.
17. Let's do that. Okay. The key is it says required. And what that means is that without that, it will not work. Because some of these, it'll work better if it has that, but it'll still work without it. Okay. So number 1, standard temperature and pressure, you don't have to have that. You can, some reactions might be work better at a given temperature than another, but it doesn't have to be standard. Okay. Number 2, catalyst, that'll definitely make it go faster, but it'll still happen without a catalyst. So it's not necessary to make it happen. You see what I mean with that part? Okay. 3 is the important one. This is the those 2 like metal cannonballs that I had in class when I smashed them together and they sparked. You had to hit them together correctly. If I didn't hit them together right, they wouldn't go. So this is all collision theory. It's number 3. With number 4, you don't have to have equal numbers. You have, because like look at water. When you make water, it's 2 hydrogens and 1 oxygen. That's not even numbers. You need the correct number, but it doesn't have to be even. So that's why it's number 3. Cool beans? Yeah, and if at any point, if you need to go to the bathroom or anything like that, I don't think there's a test going on, so you're okay. You can head out, and I don't know if the bathrooms up there are open, but you don't have to ask. Just don't go like, looting the school. That'd be bad. So I think we're through 30. Let's go here and then in the back. So yes, sir. 27. Woo! Which compound you call? Okay. So this first part here, yielding hydrogen ions, that's H+. So really this is asking me for an acid. Okay. And they kind of made it easy and they kind of made it tough. Do you happen to have a reference table?
Yeah.
Okay. If you flip to table K, which is the common acids, you just want to find the 2 that are on that table is the easy way this works. The other thing that I'm looking at is number 1, they both start with H. That's kind of the indicator that it's an acid. I know ammonia is a base, and it's listed on the base thing. As for this number 2, wow, I just spit everywhere. That was disgusting. I'm so glad you didn't see that on camera. I could have probably just played it off and no one would know, but now you all know. Yep, that's me. The problem is this is a salt, right? So that's why number 2 doesn't work. All about number 1.
When I asked compound yields hydrogen ions, does that truly mean when you combine the 2?
No. What this is all about is H2CO3 makes 2H plus CO3 2 minus. It produces H plus when it's put in water, because that's that aqueous solution part. So yeah, it's not that you're putting the 2 together. It's that when you put either one of those independently in water, it breaks off as H plus. And so now in the back. Sorry? 26. Oh, right above. Oh, they didn't make this easy. Okay, electrolytes, acid, base, salt. It's got to be one of those 3, right? So I'm looking, those are bases, okay? organic stuff, which is the carbon, that's not going to work. Okay. The tricky part here is they did this, which makes me think base. But like we talked about, if it has carbon, it's not a base. It's probably an alcohol. When it's an acid, not that I expect you guys to remember this, is that's an organic acid when you see that. None of these have it. So that means these are all alcohols. So choice 3 is going to be my answer because that's also an acid, right? So recapping with this, when they ask about an electrolyte, it has to either be an acid, a base, or a salt. So acids are either going to be something that starts with an H, or that one crazy one that they have, it's like a C2H. Oh, I don't remember. It's on your reference tables though, under organic acid. I just can't come up with it offhand. Acetic acid rather, vinegar. So that's acid. Bases are OH, but no carbon. And salts are anything that's ionic that doesn't have H as the plus and OH as the minus. So there's so many different things that could come into that. It's kind of easier to take things out in this case. Does that work?
How would you know which one is which one you're not? That's right. It could be an acid, base, or salt.
Any one of these 3 are all electrolytes. Yep. So you're just looking for anything that fits in there. So it's usually what I do is they're going to go with an acid or a base typically, or 2 acids or 2 bases, something like that. So I try and find like, okay, what are my acids? What are my bases? Oh, hey, carbon, that's not it. Stuff like that. Okay, we're going to go right down. So let's start. What? What?
Okay, so like the first one's not it because of the carbon right there.
Right.
So you just look for one that doesn't have carbon in it.
As long as it's not, I would ask if you see your reference tables, but I know what that's going to result in. Yeah, thank you. You can look at that organized reference table. Is that table K?
No, I actually did it off.
Okay, so the one at the bottom that has acetic acid or ethanoic acid, that's the one acid that they'll show that has carbon in it. So if it meets that formula, like they'll show it one of those 2 ways, then it's an acid.
What about the carbon and acid?
Carbonic acid?
Yeah.
Yeah, that one will work. That'll be okay. I guess I forgot about that one. Yep. Good.
And I just thought it was choice 1.
And it's because that's an alcohol. That's why. Yeah. Is anything else dealing with this question? Okay, that's what I thought. So let's go far in the back and then we'll kind of zigzag up and down. 28.
Yeah.
Okay.
Yeah.
Sounds good. 28. Oh, right on. So really, shoot. I feel like I talked to someone about this at some point. I just don't remember. Okay, so what this is all about is nuclear chem. And we didn't spend a whole lot of time on this one. But remember, in all the classes, we talked about things are either stable or unstable, right? And if they're stable, guess what they're going to do? Stay exactly the way they are. So are they going to either give off or absorb anything if they're stable? No. So 1 and 2 are out, right? 3 and 4, that can be a little bit easier because the only difference between those 2 is does it absorb alpha particles or does it emit alpha particles? Well, in radiation, it always gives off stuff. That's the definition of radiation, is that it gives off stuff, right? So it's going to be number 4. It's unstable and it spontaneously emits alpha particles.
So how do you know if it's radiation?
Because it's uranium, yeah. Really, like everything above atomic number 84, excuse me, is radioactive. So yeah, all the big ones, for sure. For sure. Cool. So how about in the front? Did you have one?
I was 28.
28? Okay, how about then you?
Can you go back to 21?
21. Oh. Okay, so here's what I can tell you with this. They try to make your life a little bit easier in that they italicize words that are important, right? So like boldface and italicized means important stuff because it is 20. Yep, we'll do 20 in a second. So, uh-oh. What's going on? There we go. So it's important because it says not. So I'm looking for the one that's false. So the phase of matter of a molecular substance is not determined by, it's absolutely determined by the arrangement of molecules. If they're packed tightly together, it's going to be a solid. If they're loose, it's going to be a gas. So number one is out. Number two is also out because how strongly the things are held together is what determines what phase they're going to be. So that doesn't fly. Number three, I kind of like that one. It doesn't matter how much stuff's there. It's still going to do the same stuff. And number four is out because the structure of the molecules is what determines, again, what phase it is. So this is definitely number three on that one. So does that help?
Yep.
Okay. So what I'm going to do, because it was asked, number 20 was asked. And this is a good point to review. So gas directly to a solid. Let's see. What's the number? Do you guys remember what number one means? Fusion?
Yeah.
It's what?
Not the
It's
answer.
when they combine.
Okay. It's taking smaller atoms and making them into a larger atom. So fusion is out. How about deposition? What's that?
Going from a gas to a solid.
That's the one. It's going from a gas to a solid. What about saponification? Making soap, right? And the reason they put that in there is because most people in a hurry are going to read saponification and think
So,
sublimation, right? Even though it's still wrong, that's what they're going to think. And then decomposition, that's when you break stuff apart, right? So gas to a solid is deposition, and the opposite, solid to a gas, would be sublimation. So there's that one for you. Thank you for tuning in, by the way. Others through, I think we're through 30. Let's go in the front, and then we'll go sides. I don't know which side yet. We'll flip a coin. Yes, ma'am.
number 24.
24. Which element has, oh, yeah. Okay. So it's carbon. I know that doesn't totally help.
I'll just reread the question about 20 times and remember that.
Right. Well, and it's the only one that can do, it's the only one that can make rings.
Okay.
Is really what it comes down to. We definitely know it's not hydrogen
Okay.
because hydrogen can only make one bond. So that's not going to happen. It's probably not going to be oxygen because, I mean, you would think then it would do something like this.
It doesn't.
And the problem is oxygen can only make two bonds. So there's nothing else to connect in there, and that's just weird. And aluminum makes networks, but it doesn't make rings. So it's carbon.
Okay.
Anytime it talks about making rings, that's carbon. Yeah. And then let's go back there and then over here. Yes, sir.
On 29.
Uh-huh.
Is it beta or gamma?
Yeah, which direction?
Gamma.
It's gamma.
Yeah, it's alpha particle is the weakest, beta particles in the middle, and gamma is the strongest. Gamma can go through the earth.
Okay.
Positrons are crummy. They're about the same as a beta particle. And then protons are, I don't know, they're probably somewhere between an alpha particle and a beta particle. So was that yours as well?
No.
Okay, so what was yours?